Picture a quiet, serene night. You gaze up at the sky, blanketed by a myriad of stars, each a distant sun, perhaps warming worlds of its own. Now, imagine that one of those bright pinpricks you observed just yesterday has simply vanished today. Not faded away, not blown up in a brilliant flash, but gone, as if wiped clean from the celestial canvas. Sounds like the opening chapter of a science fiction novel, right? But what if I told you this isn't fiction? It's a real astronomical enigma that has baffled scientists across the globe. Today, we are journeying to the very edge of our cosmic understanding to investigate the mystery of a star that disappeared virtually overnight. This is a story of cosmic detection, of the silent demise of a stellar giant, and a stunning discovery that could fundamentally change everything we know about the stellar life cycle. Get ready as we dive into one of the most intriguing puzzles of the 21st century. Before we get to the vanishing act itself, let's take a quick refresher on how stars actually live and die. This context is crucial for understanding why a simple disappearance is such a profound anomaly. For most of its existence, a star like our Sun peacefully fuses hydrogen into helium in its core. This process, called nuclear fusion, releases vast amounts of energy, allowing the star to shine and fight off the immense gravitational force trying to crush it. But fuel isn't infinite. Once the hydrogen in the core runs out, the star begins fusing helium and then heavier elements. Its ultimate fate depends on its mass. Sun-like stars shed their outer layers at the end of their lives, forming a beautiful planetary nebula, leaving behind a small, dense, hot core called a white dwarf, which will cool for billions of years. But for massive stars, those tens of times heavier than the Sun, things are far more dramatic. Their ending is a spectacular show. When their core runs out of fusion fuel, gravity finally wins, and the star collapses violently under its own weight. This collapse triggers a powerful explosion known as a supernova. For a brief period, a supernova can shine brighter than its entire galaxy, scattering heavy elements throughout space, the very elements that form new stars, planets, and even you and me. What remains after the blast is either a super-dense neutron star, or, if the star was exceptionally massive, a black hole. Remember that scenario: collapse, explosion, and an intensely bright flash. This is how, according to all known laws of physics, stellar giants are supposed to die. Now picture the sheer shock of astronomers when one such giant decided to break all the rules and simply exit the stage silently, leaving behind neither a farewell bow nor a blinding flash. Our story begins in a galaxy that has long been a subject of intense scrutiny for astronomers. It's officially designated as NGC 6946, but it has a much more poetic nickname, the Fireworks Galaxy. Situated about 22 million light-years away from us in the constellation Cepheus, this galaxy earned its moniker for a very good reason. Supernovae erupt there with incredible frequency, roughly 10 times more often than they do in our own Milky Way. In the last century alone, astronomers have recorded 10 such cataclysmic explosions. This makes it the perfect natural laboratory for studying the final stages of a massive star's life. Astronomers keep it under constant watch, literally waiting for the next celestial spectacle. And it was there, within this stellar metropolis, that our protagonist resided, a star destined to become a central mystery for an entire generation of scientists. Its official designation is NGC 6946 BH1. This was no ordinary star. It was a true titan, a blue supergiant. Estimates put its mass at roughly 25 times that of our Sun, and its luminosity was hundreds of thousands of times greater. If a star like this were positioned where our Sun is, its surface would extend far beyond the orbit of Earth, and its light would instantly incinerate all the inner planets of our solar system. It was a genuine powerhouse, doomed to a short but incredibly brilliant life, followed, as everyone expected, by a spectacularly violent death. Between 2001 and 2007, astronomers monitored it using various telescopes, both ground-based and orbital. It appeared stable, intensely bright, and gave no hint of the cosmic drama to come. It simply existed, like billions of other stars, waiting for its final moment, which, by cosmic standards, was fast approaching. Yet, nobody could have predicted that its finale wouldn't be a deafening blast, but a quiet, mysterious disappearance that would force scientists to re-examine the fundamental laws of stellar evolution. The mystery began in 2009, when astronomers first noticed something strange. The first real surprise came in 2009 during routine observations of the fireworks galaxy. Star N6946 BH1, previously a model of predictable stellar behavior, suddenly and dramatically began increasing its brightness. Within a few months, it shone about 1 million times brighter than our own Sun. The event looked like an outburst, but it was far weaker than a true supernova explosion. This behavior isn't entirely unique in the universe. Astronomers are familiar with luminous blue variables, extremely massive and unstable stars that periodically shed their outer layers in violent outbursts. These events, sometimes dubbed pseudo-supernovae, can dramatically increase a star's luminosity for a period. Eta Carinae in our own galaxy is perhaps the most famous example. Scientists hypothesize that this was exactly the process they were watching. Perhaps the giant star had simply coughed, ejecting some of its material into space before settling back down. This hypothesis seemed perfectly plausible and neatly explained the observed phenomenon. Astronomers continued monitoring the star, expecting that after the peak brightness, it would gradually return to its former luminosity. And it did, but only in part. Over the next few years, the star did begin to fade. Everything was following the script. Then, however, something happened that nobody had predicted. By 2015, the star hadn't just returned to its original brightness. It continued to dim until it completely vanished from view in the optical range. Where a bright blue supergiant had been shining just a few years earlier, there was now only a void. Even the Hubble Space Telescope, with its incredible visual acuity, could no longer detect it. It was a profound shock. A star with the mass of 25 suns doesn't simply dissolve into space. This violates one of the most fundamental laws of physics, the conservation of mass and energy. Where did all that matter go? Where did all that energy vanish to? It was like a disappearing act, but on a cosmic scale. Scientists were faced with a puzzle comparable to investigating the perfect crime. The scene is set, the victim is missing, but there is no body, no weapon, and absolutely no obvious evidence. So, the star vanished. The first and most obvious thought that occurred to astronomers was that they must have missed something. Perhaps the supernova explosion did happen after all, but somehow they just hadn't noticed it? That seemed highly unlikely, considering the fireworks galaxy is under constant, heavy surveillance. The explosion of a star of this mass should have been an incredibly bright event, visible for months. Missing something like that would be nearly impossible, but science demands that all versions, even the most obvious ones, must be checked. Scientists meticulously reviewed the observation archives from that period. They found no trace of a bright flare characteristic of a supernova. This confirmed there was no classic explosion. This led to a second hypothesis. What if the star hadn't vanished at all but was merely hiding? We know that stars, especially in their late stages of life, can shed vast amounts of material, creating dense dust clouds around them. Perhaps that flare observed back in 2009 was just such an emission. This cloud of dust could have become so thick that it completely obscured the star from our telescopes, absorbing all of its visible light. This theory was elegant. It didn't require inventing new physics. Cosmic dust is, after all, a very common phenomenon. However, this version had a critical flaw. Dust that absorbs the star's visible light should heat up and begin to intensely radiate in the infrared spectrum. It's like covering a hot light bulb with a thick blanket. The blanket itself will get warm and radiate heat. To test this hypothesis, astronomers pointed the Spitzer Space Telescope, which specializes in infrared observation, at the location of the missing star. They fully expected to see a bright source of infrared radiation, that very heated dust veil. But once again, the observation results were unexpected. Yes, there was some excess infrared emission recorded at that spot, but it was far too weak to be explained by a giant star hidden behind a dense dust cloud. This meant the dust veil theory didn't hold up either. The star truly was gone, and no amount of dust was hiding it. The mystery was only getting deeper. When simple and obvious explanations fall short, scientists have to turn to more exotic and audacious ideas. One such idea, which began gaining traction among astrophysicists, sounded truly revolutionary. What if we were witnessing the birth of a black hole, not through the fiery cataclysm of a supernova, but through a quiet, unseen collapse? This concept was dubbed a failed supernova, or complete collapse. Let's break down exactly what that means. In the standard model, as we know, the collapse of a massive star's core generates a powerful shockwave which blasts the outer layers of the star away, resulting in an explosion. But what if that shockwave isn't strong enough to overcome the star's monstrous gravity? In that case, there would be no explosion. All the star's matter, its entire outer envelope, would simply follow the core and fall directly into the newborn black hole. Instead of a grand cosmic fireworks display, we get only a quiet implosion. The star would simply vanish from sight, swallowed by its own gravity. For a long time, this theory existed only on paper, purely as a theoretical possibility. Nobody had ever observed anything like it. It was thought to be an extremely rare event, if it was possible at all. But the disappearance of the star N6946 BH1 fit this scenario perfectly. The flash observed in 2009 could have been the star's death throes. Perhaps this was the moment the core collapsed, releasing some energy in the form of neutrinos. This neutrino burst might have briefly invigorated the star's outer layers, causing them to expand and brighten. But there wasn't enough energy for a full-fledged explosion. Following that brief flash, all the star's remaining mass plunged after the core into the gravitational abyss. The faint infrared radiation recorded by the Spitzer telescope also finds its explanation in this model. This could be residual heat from the material falling onto the black hole. It heated up as it fell, but nowhere near the intensity generated by a supernova explosion. Thus, the failed supernova hypothesis elegantly accounted for all the observed facts: the initial brief flash, the subsequent disappearance in visible light, and the weak residual infrared glow. For the first time, scientists had a strong candidate for the role of the first documented failed supernova in history. The failed supernova hypothesis is certainly compelling, but science demands more than just a neat theory. It requires concrete proof. So, besides the star's disappearance itself, what other evidence suggests it collapsed directly into a black hole? One key piece of evidence comes from the analysis of the precursor flash that occurred back in 2009. Scientists meticulously studied its spectrum and brightness. What they found was that this flash resembled neither a classic supernova nor a typical outburst from a luminous blue variable star. Its energy was too low for the former and too high for the latter. It existed somewhere in the gray zone, a middle ground that aligns perfectly with theoretical models describing a star's death throes just before complete collapse. Another important clue is the nature of the residual infrared emission. Over time, its temperature and brightness have been slowly decreasing. This fits the model where the material ejected during the initial flash gradually cools down as it expands into space. If a hot star were hiding behind that expanding cloud, the infrared emission would remain stable or even increase. Instead, we observe fading, like the cooling embers of a cosmic fire that never fully caught light. Furthermore, scientists searched for other potential signatures. For instance, the collapse of a star's core should release a tremendous burst of neutrinos, tiny particles that barely interact with matter. Dedicated detectors, like Super Kamiokande in Japan or IceCube in Antarctica, are designed to catch these particles. Theoretically, if a strong neutrino burst had originated from the fireworks galaxy in 2009, it would have provided irrefutable proof of a core collapse. Unfortunately, no directed burst was recorded. This doesn't invalidate the theory, however. It's possible the burst was too weak or its trajectory simply didn't align with the placement of the detectors. Nevertheless, the combination of available data, the star's disappearance, the unique character of the preliminary flash, and the decaying infrared glow makes the failed supernova scenario the most probable explanation. It's like a detective novel. There are no eyewitnesses, but the circumstantial evidence is so abundant and consistent that there's almost no doubt left about the identity of the perpetrator, in this case, gravity. If the failed supernova hypothesis holds true, it has profound implications for how we understand the cosmos. Firstly, it suggests a completely new mechanism for black hole formation, one we had never observed before. We've always assumed that black holes are born in the fiery aftermath of supernovae, announcing their arrival with a spectacular bang. But now it seems they can also emerge in silence, slipping into existence unnoticed by the rest of the universe. This forces us to re-examine the so-called missing supernova problem. Based on the number of massive stars we observe and the subsequent number of neutron stars and black holes we estimate should exist, we are consistently observing far fewer supernova explosions than expected. Where are the rest of them? It's possible they are becoming these failed events, simply collapsing directly into a black hole without putting on any kind of light show. If this is true, the sheer number of black holes in the universe could be far greater than we ever imagined. They might be lurking everywhere we least expect, born from stars we simply thought had just faded out. Secondly, this discovery fundamentally impacts our understanding of the universe's chemical evolution. Supernovae are the primary cosmic factories for manufacturing heavy elements, things like oxygen, iron, and gold. It is the scattering of these elements throughout the galaxy that ultimately makes rocky planets and life possible. If a significant fraction of massive stars fails to explode and instead collapses, they drag all their newly forged heavy elements with them into the black hole, effectively removing them permanently from the galactic recycling process. This means the universe is being enriched with heavy elements at a slower pace than our current models predict. We will have to fundamentally revise galaxy chemical evolution models to account for this new channel of material leakage. Thus, a single event, the silent disappearance of a star in a distant galaxy, has the potential to trigger a chain reaction, forcing a major revision across entire fields of astrophysics. This is a powerful illustration of how science truly operates. A single observation that simply doesn't fit the established narrative can shatter old dogmas and open up entirely new horizons for discovery. The universe has, once again, proven itself to be far more complex and interesting than even our wildest theories dared to suggest. Let's take a slight detour from the central theory and explore some alternative explanations, however improbable they may seem, for this puzzling celestial event. Science must always remain open to alternative hypotheses, no matter how fantastic they appear at first glance. One such hypothesis involves an exotic type of star known as a Thorne-Zitkov object, or TZO. This is a purely theoretical stellar model describing a red giant or supergiant that hosts a neutron star at its core instead of a conventional nucleus. This kind of hybrid could potentially form, for instance, from the merger of two stars within a close binary system. TZOs are predicted to have very specific chemical signatures and would be inherently unstable. Perhaps what we observed was the collapse of exactly such an object. Its death might deviate from the standard supernova scenario, leading to a much less conspicuous outcome. However, the Thorne-Zitkov object remains strictly theoretical. We currently lack compelling observational data to confirm its existence. Another, far bolder idea takes us straight into the realm of science fiction. What if we are witnessing the manifestation of advanced extraterrestrial activity? The concept of the Dyson sphere, proposed by physicist Freeman Dyson, suggests that a highly advanced civilization could build a gigantic structure around its star to capture all its energy output. If such a sphere were constructed around star V6946 BH1, it would completely obscure the star's visible light. The sphere itself, heating up from the energy absorption, would then radiate in the infrared spectrum. This theoretically aligns with some of our observations. However, this hypothesis runs into immediate problems. Firstly, applying Occam's razor, we shouldn't invoke complex entities without extreme necessity. A failed supernova is a natural explanation rooted in established laws of physics. Alien activity is a far stronger and, crucially, currently unsubstantiated assumption. Secondly, the sheer speed at which the star vanished suggests a catastrophic natural process rather than systematic construction. Building a structure the size of a stellar system would require immensely more time. These are admittedly purely speculative musings, but they demonstrate just how much this event continues to stir the scientific imagination, pushing us to think far beyond conventional boundaries. But let's get back to the main question. What actually determines the fate of a massive star? Why does one explode as a brilliant supernova while another quietly collapses into a black hole? The answer, apparently, lies in the structural details of the star during the very last stage of its life, literally moments before the final collapse. Several factors likely play a key role. The first, and most significant, is the star's mass. There is likely a critical mass threshold. Stars lighter than this threshold explode, while those heavier than it directly collapse. Estimates place this threshold anywhere between 20 and 40 solar masses. Our missing star at 25 solar masses sits right in this borderline region, making it an ideal candidate for a failed explosion. The second important factor is the star's rotational speed. A rapidly spinning star possesses a high angular momentum. During collapse, this momentum can help kickstart the explosion by creating centrifugal forces that resist gravity. Conversely, a slowly rotating star may be much more prone to direct collapse. The third factor is metallicity, the abundance of elements heavier than hydrogen and helium. Metallicity affects the opacity of the star's outer layers and the intensity of the stellar wind that sheds mass throughout its life. A low metallicity star might retain more mass by the end of its life, significantly increasing its odds of a direct collapse. Finally, the structure of the pre-supernova core itself is hugely important. The distribution of density and temperature in the star's central regions in the final seconds before collapse can be the deciding factor. Tiny structural differences can lead to drastically different outcomes, a successful explosion or a complete failure. The problem is that we can't look inside a star to see these fine details. All we can do is build complex computer models that attempt to replicate these processes. And the disappearance of N6946BH1 is an invaluable gift to theoretical physicists. It provides a real-world experimental result against which we can now check our models, helping us rule out incorrect theories and refine the accurate ones. This is a key to understanding one of the most fundamental and dramatic processes in the universe. Let's now discuss the future of this intriguing scientific investigation. The story of the star N6946BH1 is certainly far from finished. Scientists are still keeping a close eye on the exact location where it used to reside. What exactly are they hoping to observe? One key area is the ongoing evolution of the infrared source. If this is truly just a cooling cloud of matter ejected prior to the collapse, it should continue to fade and cool according to predictable scientific laws. Any deviation from this prediction would be a huge prompt to revise the current theory. For instance, if the source suddenly brightens again, it could signal that something far more complex than simple cooling is taking place. Another possibility involves the difficult task of directly detecting the newborn black hole. This is incredibly challenging because a black hole emits no light itself. However, we can observe its indirect manifestations. If the vanished star had a companion, another star, orbiting it, that companion star would now be orbiting the invisible black hole. By tracking the companion star's movement, scientists could calculate the mass of the unseen object and finally confirm the presence of a black hole. So far, no signs of a companion have been found, but the search is far from over. Further hope rests with future telescopes. Projects like the James Webb Space Telescope, with its unparalleled sensitivity in the infrared spectrum, can provide a far more detailed picture of what exactly is happening at the site of the missing star. Perhaps Webb will be able to resolve subtle details within the residual radiation spectrum, details that could ultimately confirm or disprove the collapse hypothesis. Furthermore, astronomers are now actively searching for similar events in other galaxies. Now that we know what to look for, stars that suddenly brighten and then simply vanish, the chances of finding new candidates for failed supernovae are significantly increasing. Every new discovery of this type will bring us closer to understanding just how common this phenomenon is and what role it plays in the life cycle of the universe. So, while the star itself may be gone, its scientific legacy is only just beginning to unfold. This story isn't just about a single astronomical event. It's a breathtaking illustration of the scientific method in action. It all started with an observation that simply didn't fit into the existing framework of knowledge. This baffling observation gave rise to a true mystery, a problem that demanded a solution. Scientists didn't dismiss it as a mere mistake or an anomaly. Instead, they began systematically testing every possible explanation, one after the other. They started with the simplest hypotheses, perhaps a mist, supernova, or a dense cloud of dust. Crucially, each of these hypotheses made specific, testable predictions. For instance, the dust cloud theory predicted a bright infrared emission. Scientists then conducted new observations specifically to verify these predictions. When the observations refuted those predictions, the hypotheses were immediately rejected. This is a vital point. In science, theory must conform to the facts, never the reverse. Once the simpler explanations were exhausted, they had to turn to a more complex and novel idea, the theory of the failed supernova. This theory successfully accounted for the entire set of observed facts: the initial flare, the subsequent disappearance, and the faint infrared afterglow. It quickly became the leading working hypothesis. But the process doesn't end there. The task of science now is to rigorously test this new hypothesis, subjecting it to the strictest possible scrutiny. Researchers are searching for new evidence that could either confirm it, like tracking the movement of a potential companion star, or, conversely, disprove it, for example, if the infrared source behaves unpredictably. This constant cycle of observation, hypothesis testing, and rejection is precisely how scientific progress is achieved. It is a slow, painstaking process, but ultimately, it is the most reliable path to understanding the world. And the mystery of the vanished star is simply one of the most exciting new chapters in humanity's endless book of knowledge. Let's try to imagine this from the star's own point of view. For millions of years, it existed in relative peace, fusing lighter elements into heavier ones deep within its searing hot core. At its center, shell upon shell, like an onion, the products of thermonuclear fusion accumulated: hydrogen, helium, carbon, oxygen, all the way up to iron. Iron is the final stop. Synthesizing iron doesn't release energy. On the contrary, it consumes it. And then comes the moment when a massive iron core forms at the star's heart. Deprived of an energy source, it can no longer resist the crushing force of its own gravity and begins to contract catastrophically. This entire process takes mere fractions of a second. The core, once the size of the Earth, collapses down to the scale of a small city, transforming into superdense neutron matter. This collapse unleashes a monstrous amount of energy in the form of neutrinos, generating a powerful shockwave. In a typical scenario, this wave, energized by the neutrinos, races outward, ripping the star apart. But in the case of N6-946-BH1, something went wrong. Perhaps the gravity of the iron core was simply too immense, or maybe the structure of the outer layers absorbed the entire energy of the shockwave, preventing its escape. The shockwave fizzled out, never reaching the surface, and so the star's entire outer envelope, its colossal mass of more than 20 solar masses, lost its support and began to plunge inward toward the center, onto the newly formed object, whether it was a neutron star or already a black hole. This process was not instantaneous. Matter fell in, layer after layer. A small amount of material may have been expelled by the initial impulse of the core collapse. That was the faint flash we observed back in 2009. But the bulk of the mass was doomed. It streamed into the gravitational trap, heating up and radiating in the infrared spectrum until its last atom finally crossed the event horizon. Where there had once been a giant blue sphere of searing plasma, only a point of singularity remained, hidden from the rest of the universe. The star had committed the quietest suicide in the history of observable astronomy. It's fascinating to draw a parallel between the history of our vanished star and another famous astronomical object, Eta Carinae, which we've already discussed. Eta Carinae is a massive and incredibly unstable stellar system right here in our own galaxy. It's roughly 100 times the mass of our Sun and shines 5 million times brighter. In the mid-19th century, Eta Carinae experienced the so-called Great Eruption. For about 20 years, it was the second brightest star in the night sky before abruptly dimming. This eruption expelled a colossal amount of material into space, forming the famous homunculus nebula that surrounds the star. Initially, the 2009 flare from N6946BH1 seemed like a similar eruption. Many astronomers initially assumed this was the case. They expected that, much like Eta Carinae, the star would survive the cataclysm and eventually become visible again. But the key difference lies in what happened next. Eta Carinae, though it faded, never vanished. We still see it clearly at the center of the nebula, and it remains one of the most massive and luminous stars in the galaxy. It survived. Our star, however, did not. After its flash, it disappeared completely. This comparison clearly shows that we observed two fundamentally different processes. The Eta Carinae flare was a manifestation of instability, not a death throw. The star shed some of its mass, but its core remained intact, and thermonuclear fusion continues within it. The flash of N6946BH1, however, appears to have been directly linked to a core collapse. It was a final breath, followed by complete and definitive death. Perhaps these pre-death flashes are the defining characteristic of failed supernovae. By studying them, we might learn to predict which stars will explode and which ones will simply fade quietly into oblivion. It's possible that Eta Carinae itself, when its time comes, won't explode either, but will follow the example of its distant sister in the fireworks galaxy. One of the most intriguing aspects of this whole story is how it forces us to confront the very limits of our observation. We are accustomed to studying the universe by tracking the light that reaches us from distant objects. Supernova explosions, brilliant quasars, glowing nebulae, these are all loud, spectacular events that are easy to spot. But what if the most important and common processes in the cosmos are actually silent and invisible? The disappearance of a star is an event easily missed. If we hadn't been continuously monitoring the fireworks galaxy, we never would have known that star existed in the first place, much less noticed its vanishing act. How many other such silent deaths are occurring throughout the universe, completely unnoticed? It's possible that direct collapse into a black hole isn't a rare exception, but the default outcome for the most massive class of stars. If this is true, then our current estimates of the black hole population might be drastically underestimated. We usually search for black holes either by observing their gravitational influence on nearby stars or by detecting the powerful radiation from accretion disks as they consume matter. Both of these methods only work under specific conditions, but if a black hole is born alone, from a solitary star, with no surrounding matter to feed on, it will be completely invisible. It would simply travel through the void, revealing itself only through gravity. Studying failed supernovae gives us a powerful new tool for locating these objects. We shouldn't be looking for the black holes themselves, but rather the events of their birth, those disappearing stars. This opens up a brand new field in astronomy, one that could be called the astronomy of absence, or transient astronomy. We aren't looking for what appeared, but rather for what vanished. This fundamentally new approach could lead to revolutionary discoveries. Perhaps in the coming years, with the deployment of powerful new survey telescopes like the Vera C. Rubin Observatory, we will be logging dozens, even hundreds, of such disappearances annually. If so, the failed supernova will transition from an exotic hypothesis into a routine and well-studied phenomenon. Let's return to the topic of neutrinos. As we mentioned earlier, the collapse of a star's core should trigger an incredibly powerful burst of these particles. In fact, neutrinos carry away 99% of the total energy released during the collapse. Only 1% remains to fuel the subsequent supernova explosion, or, as in the case we are discussing, not to fuel it. These neutrinos pierce through the entire star and escape into space virtually unimpeded, carrying vital information about the deepest processes happening within the core. It's like having the perfect spy, one capable of penetrating the most heavily protected bunker and retrieving every secret inside. Capturing these neutrinos is the holy grail for any astrophysicist studying supernovae. In 1987, we succeeded. Neutrino observatories on Earth recorded about 24 neutrinos from the explosion of supernova 1987A in the Large Magellanic Cloud. This event marked the birth of neutrino astronomy and served as a triumphant confirmation of our core collapse theories. In the case of our missing star, as noted, no neutrino burst was ever recorded. But what does that actually imply? The distance to the fireworks galaxy is 140 times greater than the distance to the Large Magellanic Cloud. Since the neutrino flux weakens with the square of the distance, this means that even if the burst had the same power as supernova 1987A, our current detectors would be lucky to register 1 or 2 neutrinos and most likely 0. Therefore, the lack of a signal doesn't prove the lack of an event. Instead, it presents us with a massive, ambitious challenge: building the next generation of neutrino telescopes, instruments sensitive enough to register core collapses in distant galaxies. If we can achieve this, we will gain a unique tool. We will be able to see not only the bright explosions of supernovae, but also the silent collapses that produce no visible light flash. We can finally create a complete census of all massive stellar deaths, not just the ones that decided to put on a show. Neutrino astronomy holds the ultimate key to unlocking the mystery of failed supernovae and allowing us to look deep into the heart of a dying star. Let's look at another angle of this story: the chemical composition of the vanished star. Before its disappearance, the star was classified as a blue supergiant, a type characterized by extremely high surface temperatures and a powerful stellar wind. By analyzing the star's spectrum before it vanished, astronomers were able to determine its chemical makeup. Crucially, they found it was relatively metal-poor. This could be a vital clue. As previously discussed, low metallicity stars shed less mass throughout their lifespan, meaning they retain a more massive core leading up to the moment of collapse. This, in turn, significantly increases the likelihood of a direct collapse into a black hole. Therefore, a star's chemical composition may act as a key prognostic indicator of its ultimate destiny. Perhaps there exists a kind of map of stellar destiny for massive stars, where initial mass is plotted on one axis and metallicity on the other. In one region of this map are stars destined to explode as classical supernovae, in another, those that result in a failed supernova, and perhaps a third region holds those that explode as hypernovae, generating powerful gamma-ray bursts. Our vanished star, N6946BH1, became the first data point plotted onto this map, squarely in the quiet collapse zone. Now, the main goal for astronomers is to find other similar objects and populate this chart, allowing us to determine precisely which combination of stellar parameters leads to which final outcome. Understanding this will not only improve our grasp of stellar physics, but also allow us to more accurately model galactic evolution. The reason is simple. Whether a star explodes or silently collapses dictates how many heavy elements are ejected into the interstellar medium, thereby becoming available for the next generation of stars and planets. A star's chemical composition is essentially its genetic code, largely predetermining both its life trajectory and its ultimate dramatic fate. Let's visualize the star's final moments. Thousands of years before the ultimate collapse, its core had already burned through its hydrogen fuel, followed by helium, carbon, and oxygen. Each successive fusion stage occurred faster than the last, requiring increasingly extreme temperatures and pressures. The final stage, the burning of silicon into iron, lasted only a few days. At this point, the star was already doomed. Its outer layers still shone, seemingly undisturbed, but in its heart, the clockwork of a gravitational time bomb was already ticking. When the iron core reached critical mass, the collapse began. Imagine a sphere the size of Earth, which, in the span of a tenth of a second, is crushed down to the size of a city like Moscow. Density at the center reached unimaginable values, exceeding that of an atomic nucleus. Protons and electrons merged, forming neutrons and releasing a massive flood of neutrinos. This neutrino flux rushed outward at near light speed. It was this flux that likely triggered the brief flash we observed. It imparted a fraction of its energy to the outer layers, causing them to suddenly expand and brighten. But that initial impulse wasn't enough. The gravity of the newborn central object, by now most likely a black hole, was simply too powerful. The shock wave that should have torn the star apart stalled deep within its interior. And then the great infall began. The star's unsupported outer layers plunged down into the gravitational funnel. First came the layers rich in silicon and oxygen, followed by carbon, helium, and finally the vast outermost envelope of hydrogen. This process could have lasted several years. During this time, the falling matter heated up and radiated energy, not in the visible spectrum, but in the infrared. It was a slow, silent swallowing. Year after year, telescopes on Earth recorded the visible light of the star fading away, while the infrared source slowly cooled. By 2015, the last remnants of the gigantic star had crossed the event horizon. Where a blue giant had shone for millions of years, only emptiness remained, and gravitational ripples spreading across the fabric of space-time. Silence. This story also forces us to consider our place in the universe and the true nature of time. We often say a star vanished overnight or in a few years. But we must remember that the events we are observing happened 22 million years ago. That is how long it took for the light and the information about the star's disappearance to travel from the fireworks galaxy all the way to our telescopes. When we looked at that star back in 2007, seeing it bright and stable, in reality, it had already been gone for 22 million years. It had long since collapsed into a black hole. We were merely observing its ghost, a light echo from the distant past. The actual news of its death, the final collapse, only reached us in 2009 in the form of that brief, defining flash. It's an astonishing realization, to be a witness to events that are already deep history. All of astronomy is, essentially, a time machine, allowing us to peer directly into the past. The farther out into the cosmos we look, the more ancient the epochs of the universe we are viewing. When we observe the Andromeda galaxy, we are seeing it as it was 2.5 million years ago. When we look at distant quasars, we are witnessing the universe in its infancy, when it was only a few billion years old. And in this context, the disappearance of star N6946. BH1 is far more than just an astronomical curiosity. It is a message from the past that forced us to fundamentally rethink the present and future lives of stars. It is a profound reminder that the universe operates on its own, vastly different timescales. We are merely tiny observers on a small planet, granted the brief privilege of gazing into this abyss of time and space, attempting to unravel its greatest mysteries. What other cosmic objects might exhibit this kind of sudden disappearance? While the failed supernova is the leading candidate, there are other, more hypothetical scenarios we must consider. For instance, some theories propose the existence of black stars or gravitational vacuum stars. These are theoretical alternatives to standard black holes. According to these models, when a star collapses, instead of forming a singularity, it transitions into a novel state of matter, stabilized and held together by quantum gravitational effects. A black star would be nearly indistinguishable from a black hole from the outside, but it lacks the classical event horizon. Crucially, such an object is not eternal. After an incredibly long period, it might suddenly explode, releasing all the matter it previously consumed back into the cosmos. Could we be observing not a collapse, but rather a catastrophic event related to one of these exotic objects? While intriguing, this is highly unlikely, as it plunges us deeply into the realm of purely speculative physics. Another possibility is a direct stellar collision. In dense star clusters, such events do happen. If two massive stars collide, the result could be their merger, followed immediately by a rapid collapse into a black hole. However, the firework galaxy is not a globular cluster, and its stellar density is simply not high enough to make collisions a frequent occurrence. Furthermore, a collision would be accompanied by a very specific, observable light flare, which was entirely absent in our observations. Therefore, despite these alternative ideas, none of them fully account for the totality of the observed facts, as well as the failed supernova hypothesis. It remains the most straightforward, logical, and physically sound explanation. This is a classic example of how a scientific theory, even one initially developed purely through speculation, can find powerful confirmation in observation, fundamentally changing our understanding of the cosmos. What was once just an equation on a chalkboard has now become a concrete reality, playing out before our eyes in a distant galaxy. Let's talk about the name that has stuck to this star and others like it, the failed supernova. This term is, of course, highly anthropomorphic and not entirely accurate from a purely physical standpoint. The star didn't try to explode and then fail. It simply followed the laws of physics, which, in its particular scenario, led directly to this outcome. For the universe itself, there are no successful or failed results, only different pathways of stellar evolution. Nevertheless, the term perfectly captures our surprise and, in a way, our disappointed expectations. We, the observers, anticipated a spectacular show filled with dazzling special effects, but all we got was the quiet disappearance of an actor walking off stage. But perhaps this failure holds a deeper meaning. A supernova explosion is an act of creation. It scatters life's essential elements throughout the cosmos. A quiet collapse into a black hole, however, is an act of cosmic selfishness. The star takes all of its wealth, all the heavy elements it forged, with it into an irrevocable grave. It refuses to share its treasure with the galaxy. If the universe contains many of these selfish stars, it could slow down the process of enriching the interstellar medium, consequently making the conditions for life's emergence much rarer. On the other hand, the birth of a new black hole is also a profoundly significant event. Black holes play a crucial role in the formation and evolution of galaxies. Supermassive black holes in galactic centers govern star formation processes. Meanwhile, stellar mass black holes merging with one another generate gravitational waves that carry information from the universe's most extreme corners. So perhaps what is a failure in terms of chemical evolution is actually a success in terms of gravitational dynamics. The universe maintains a dynamic balance between creation and consumption, between spectacular explosions and quiet disappearances, and, for the first time, we have the opportunity to glimpse behind the curtains of this eternal cosmic drama. What are the chances of such an event happening right here in our own galaxy, the Milky Way? They are actually quite high. Our galaxy hosts several prime candidates for becoming future supernovae, or perhaps failed supernovae. The most famous among them are Betelgeuse in the constellation Orion and the already mentioned Eta Carinae. Betelgeuse is a red supergiant that is nearing the absolute final stage of its life. Estimates suggest it could explode any moment within the next 100,000 years, or perhaps it already has, and the light from the event simply hasn't reached us yet. Its mass is roughly 15 to 20 times that of the Sun, placing it right on the boundary between a standard supernova and a complete collapse. No one can say for sure which path its demise will take. If it does explode, it will become as bright as the full moon for several weeks, visible even during the daytime. If, however, it quietly collapses, one of the brightest stars in Orion will simply vanish from our skies. This would truly be a historic event for all humanity. Eta Carinae is even more massive and unstable, but it's much further away. Its grand finale will likely be even more spectacular, though it is also harder to predict. By observing stars like these in our own galaxy, we can look for signs that indicate an approaching collapse, for instance, changes in the pulsation pattern, a rapid alteration of the surface chemical composition, or a burst of neutrinos. There is even a supernova early warning system, or SNEWS, which links neutrino detectors all over the globe. If these detectors register a neutrino burst from a core collapse within our galaxy, they can sound an alarm hours before the light from the explosion reaches Earth. This gives astronomers precious time to point every telescope in the world at the correct spot and witness the very beginning of the explosion. And perhaps one day the system will give the signal, but no explosion will follow. At that moment we will realize we have witnessed the birth of a new black hole right here in our cosmic neighborhood. Let's return to the numbers. This star had a mass of about 25 times that of our Sun. What does that mean in more familiar units? The mass of the Sun is approximately 2 nonillion kilograms. That's a 2 followed by 30 zeros. So the mass of this vanished star was 50 nonillion kilograms of matter that simply blinked out of the visible universe. Where did it go? It collapsed into a black hole. How big is this newborn black hole? The size of a black hole is defined by its gravitational radius, or the Schwarzschild radius. For an object 25 times the mass of the Sun, that radius is only about 75 kilometers. Just imagine. The entire mass of that gargantuan star, which once occupied a volume comparable to the orbit of Earth, is now shrunk down into a sphere just 150 kilometers in diameter. That's less than the distance between many major cities right here on Earth. The density of such an object approaches infinity at its central point, the singularity. Gravity at its surface, the event horizon, is so immense that not even light can escape it. That is precisely why we can't see it. It has become a gravitational prison with no exit. What's fascinating is that the flare preceding its disappearance released energy equivalent to what our Sun produces over 100,000 years, and yet that tremendous surge of energy still wasn't enough to tear the star apart. This gives us a stark glimpse into the colossal forces acting inside massive stars. The inward pull of gravity was so enormous that even the energy output of hundreds of thousands of suns couldn't overcome it. It was truly a battle of titans, and this time gravity achieved a clean and absolute victory. All these figures help us truly grasp the scale and extremity of the processes we are discussing. We aren't just talking about a dot disappearing from the sky. We are talking about the fundamental transformation of matter and energy under the most exotic conditions imaginable. Does this discovery affect the search for extraterrestrial life? At first glance, there appears to be no direct link. But if we consider the implications, the connection is certainly there. We know that the heavy elements essential for life, carbon, oxygen, nitrogen, and iron, are forged deep inside massive stars and then dispersed throughout the galaxy by supernova explosions. This stardust is what eventually forms rocky, Earth-like planets and ultimately living organisms. However, if a significant portion of the most massive stars don't explode but instead collapse directly into black holes, they fail to enrich the galaxy with these vital elements. They essentially act as greedy stars, hoarding their treasures and taking them away. This suggests that the average metallicity, the abundance of elements heavier than hydrogen and helium, in galaxies might be growing slower than we previously assumed. And lower metallicity reduces the probability of forming rocky planets, and consequently, the likelihood of life. Consequently, the frequency of these failed supernovae could become a crucial variable in the famous Drake equation, which estimates the number of intelligent civilizations in the galaxy. If non-exploding stars prove to be numerous, this discovery lowers the overall habitability factor of the cosmos. This provides yet another potential explanation for the Fermi paradox. Where is everyone? Perhaps the conditions necessary for life are simply rarer because many of the factories producing the necessary building blocks don't scatter their inventory, they just collapse in on themselves. Of course, this is just one of many variables, but it beautifully illustrates how closely linked two seemingly distant fields, stellar collapse astrophysics and astrobiology, truly are. But what can we say about the stage upon which this stellar drama unfolded? The fireworks galaxy, officially designated NGC 6946, is classified as a barred spiral galaxy. It bears a resemblance to our own Milky Way, but is defined by an incredibly heightened rate of star formation. Its spiral arms are teeming with young, hot, massive stars. This intense activity explains why it experiences so many supernova explosions. It is both a stellar nursery and, simultaneously, a stellar graveyard. The vanishing star resided in one of these very spiral arms, surrounded by countless stellar siblings. This was a bustling, dynamic environment, and it was precisely this dynamism that allowed us to witness such a rare event. Had this star been located in an old elliptical galaxy where star formation stopped millennia ago, or in a quiet, obscure corner of our own galaxy, the chances of ever spotting it would have been drastically lower. In this sense, the location of the event was no accident. The universe essentially held the performance right where the most observers with telescopes were watching. This discovery also confirms that if we want to find other similar pre-supernova events, we must prioritize searching these same types of galaxies, those actively forming stars. It is in these stellar cradles where their most dramatic, tragic deaths are most likely to occur. Studying the surrounding environment of astronomical events often yields just as much crucial information as studying the event itself. In this specific instance, the cosmic address of the vanished star provided yet another indirect confirmation that we were indeed witnessing the dramatic final act of a young, massive star. Let's take a moment to consider gravitational waves. According to Einstein's general theory of relativity, any accelerating masses must create ripples in the fabric of space-time, and these ripples travel at the speed of light. The core collapse of a massive star is one of the most powerful sources of gravitational waves in the universe. When the core collapses asymmetrically, it radiates gravitational waves, carrying away crucial information about the dynamics of that catastrophic event. For a standard, successful supernova, the resulting explosion is also asymmetric, generating a powerful, yet complex and chaotic signal. However, in the case of a failed supernova, where the star simply collapses without exploding, the gravitational wave signal is expected to be much cleaner. It should manifest as a characteristic chirp, where the wave frequency and amplitude rapidly increase as the core compresses, before abruptly cutting off when a black hole is finally formed. Detecting such a signal would provide the most direct and irrefutable evidence that a full collapse has occurred. Unfortunately, back in 2009, state-of-the-art gravitational wave observatories like LIGO and Virgo, in their current advanced configurations, had not yet been deployed. They began operations much later, but today they are fully operational, regularly detecting the mergers of black holes and neutron stars. They are also capable of detecting gravitational wave signals from supernovae in nearby galaxies. This means that if a similar stellar disappearance were to happen today, we would have the chance not only to observe it with traditional telescopes, but also to hear it using these advanced gravitational detectors. This capability marks a genuine revolution in the study of these violent cosmic events. We will be able to simultaneously gather information through both the electromagnetic, light, and gravitational wave channels. This is known as multi-messenger astronomy, and it promises to give us the most complete and detailed understanding yet of the dramatic processes unfolding in the final moments of a star's life. This brings up another interesting question. What if the entire star didn't fall into the black hole? Is it possible that a small fraction of its outer layers was actually ejected into space? Some models predict that even in a failed supernova, a small percentage of the star's mass can receive enough momentum to escape. This would constitute a kind of failed explosion, extremely weak and dim. If this is the case, we might eventually see this ejected material collide with the surrounding interstellar medium, generating a faint glow in the radio or X-ray spectrum. That would give us yet another way to confirm that a dramatic event actually took place there. The search for this kind of radio or X-ray echo is already underway, but thus far it has been unsuccessful. Perhaps the ejection was simply too weak, or the material hasn't reached dense clouds of interstellar gas yet. Regardless, this remains a fruitful direction for future research. It is also worth noting that the failed supernova scenario might not be the only pathway for a silent stellar death. There are models where the star sheds its entire hydrogen envelope before collapse due to an intense stellar wind. As a result, only its bare helium core collapses. This type of collapse may also not result in a bright explosion, but its observational signature would differ significantly from what we've previously discussed. Studying the full variety of stellar end-of-life stages is currently one of the most active fields in modern astrophysics. We are gradually realizing that the classic scenario, a bright supernova leading to a neutron star or black hole, is only one path, and that many other subtle and complex routes exist. And every new mystery, like the disappearance of star N6946 BH1, helps us paint a more complete and multifaceted picture of cosmic evolution. Picture yourself as the lead detective on this unusual case. You've got your crime scene, a specific point in the firework galaxy, and your victim, now vanished, a star weighing 25 times the mass of our Sun. The witnesses, the Hubble and Spitzer telescopes, provide their testimony. They report the victim exhibiting strange behavior first, a brief flash, and then simply vanishing, leaving behind only a faint thermal signature, or heat spot. You interview several suspects. Suspect number 1, Mr. Dust. He claims he simply threw a dense cosmic blanket over the victim, insisting the star is alive and well, merely hidden. But the forensic team, using infrared observations, proves the blanket is far too cold to conceal a star this massive. He's lying. Suspect number 2, Mr. Supernova. He claims the victim perished in a loud, brilliant explosion. However, every witness from massive sky surveys confirms they never saw the required signature flash. His story doesn't hold up. This brings us to the prime suspect, Mr. Gravity, specifically in his most terrifying manifestation, known as complete collapse. He has no alibi. His motive is simply the fundamental law of nature. His method? Quiet, ruthless absorption. And every piece of evidence points directly at him. The nature of the brief pre-collapse flash, the clean disappearance, the weak residual heat, it all aligns perfectly with his established modus operandi. You lack direct smoking gun evidence, like fingerprints, gravitational waves, or security camera footage, a neutrino burst, due to the technological constraints of the era. But the sheer totality of circumstantial evidence is so overwhelming that you are ready to issue the guilty verdict. This scenario perfectly illustrates how modern astrophysics operates, as a massive cosmic detective agency investigating the mysteries and crimes of the universe, using photons, neutrinos, and gravitational waves as its key evidence. The entire story is steeped in irony. This galaxy was named the Fireworks because of its spectacular, noisy explosions of supernovae. Astronomers were watching it, hoping to catch the next brilliant light show. Instead, they witnessed the quietest, most subtle event imaginable. It was like showing up at a massive rock concert only to hear absolute silence instead of deafening guitar riffs. The universe, in a way, played a trick on us, proving that its repertoire is far wider than we ever assumed. It doesn't just know how to scream, it knows how to whisper, and often the most profound meaning is hidden precisely in that whisper. This story teaches us to always be ready for the unexpected. We can't stick to a single paradigm and expect the universe to always behave exactly as the textbooks dictate. The greatest discoveries happen precisely when we encounter something that completely shatters our existing models. That is the true engine of science. If every observation perfectly aligned with our current theories, science would be boring and would have finished long ago. Thankfully, the universe constantly throws new mysteries our way, forcing our minds to work, create new theories, and build new instruments to test them. The mystery of the missing star is one of the best of these challenges, a gift from the universe to our curiosity. It reminds us that despite all our achievements, we are still standing on the shore of a vast, unknown ocean, and the most thrilling discoveries are still ahead. To summarize our investigation, we can state with a high degree of confidence that we have witnessed a unique event, the first reliably documented case of a failed supernova. A massive star, instead of exploding, quietly collapsed directly into a black hole. This event was predicted theoretically but had never been observed before. The flare recorded in 2009 was likely the star's pre-collapse death throes linked to the initial implosion of its core. Its subsequent disappearance in visible light coupled with faint, decaying infrared radiation are direct consequences of the star's main mass falling into the nascent black hole. This discovery is immensely significant. It reveals an alternative pathway for black hole formation, one we had not previously accounted for. This finding suggests there may be far more black holes in the universe than previously estimated. It also impacts our understanding of galactic chemical evolution, because in this scenario, heavy elements are not ejected into space. They are instead locked away inside the black hole. The story of N6946 BH1 has opened a new window onto the universe, forcing us to search not just for what appears, but also for what vanishes. This marks the beginning of a new era in the study of stellar life cycles, one where quiet, unnoticeable events may prove just as critical as the most spectacular cosmic cataclysms. And while the star itself is gone forever, its history will long continue to illuminate our path toward new knowledge about the universe's deepest mysteries. Let's take a moment to cement the main points of our journey. We started by covering the fundamentals of stellar life cycles, which helped us understand why a massive star's normal death is always marked by a brilliant supernova explosion. We then shifted our focus to the fireworks galaxy, where we met our key player, a blue supergiant behaving in a very unusual manner. We tracked its history, observing a mysterious flash back in 2009, only for it to vanish completely from sight by 2015. We quickly examined and dismissed the simple explanations like the star merely hiding behind a cloud of dust. This brought us to our central hypothesis, a failed supernova. We defined what that means. The star underwent direct gravitational collapse into a black hole without exploding, a case where gravity simply triumphs over all opposing forces. We then looked closely at the key evidence supporting this theory, the specific characteristics of the initial flash, and the residual infrared radiation signature. We discussed the colossal implications of this discovery for astrophysics. It radically alters our assumptions about the prevalence of stellar mass black holes and the way the universe is enriched with heavy elements. We even touched upon alternative, more exotic hypotheses and quickly understood why they were far less probable. We peered into the very heart of the dying star, imagining those final dramatic moments of its existence. This event, which actually took place 22 million years ago, has now opened up an entirely new way of studying the cosmos, the targeted search for disappearing objects. This was a true cosmic detective story, complete with a core mystery, compelling evidence, multiple suspects, and ultimately a highly convincing solution that nonetheless generated even more profound questions. But then again, such is the very nature of science. So, the mystery of the star that vanished overnight seems to have finally been solved. We didn't witness the grand explosion we were all expecting. Instead, the universe showed us something far more subtle and mysterious, the quiet birth of a black hole. A massive giant star, 25 times the mass of our own sun, simply flickered out, taking all its secrets beyond the event horizon. This so-called supernova failure has actually turned out to be a massive success for science. For the first time, it gave us observational proof that stars can die not just with a bang, but with a whisper. This discovery forces us to rethink the sheer number of black holes in the universe. It makes us reevaluate the rate at which the cosmos is enriched with the elements necessary for life. And crucially, It gives us a brand new tool for tracking down these most elusive objects. Now, astronomers around the world are hunting for new, failed supernovas to understand just how common this phenomenon truly is. Every vanished star we find will be one more step toward fully comprehending this astounding process. We may be on the verge of discovering that quiet deaths in the universe are just as common as the explosive ones. Thank you for spending this time with me, diving deep into this incredible cosmic mystery. I hope this lecture was not only reassuring, but genuinely captivating for you. If you enjoyed our investigation, please hit the like button on this video and subscribe to the channel so you don't miss new stories about the universe's greatest secrets. Now, for the final question for all of you, what do you think really happened to the star? Was it truly just a failed supernova, or is there something even more enigmatic behind this that we haven't grasped yet? Write your theories in the comments below. I'm genuinely excited to read them. Good night and clear skies.